Hello, my name is Catherine Farley, and I attended the Einstein's Cosmos and the Quantum public lecture by Professor Abhy Ashtekar from the Institute for Gravitation and the Cosmos at Pennsylvania State University. And the public lecture was on November 14th of this year, 2017. So, Professor Ashtekar's presentation, again, was on Einstein's Cosmos and the Quantum. And so what a lot of this has to do with is these new ideas in regards to gravitation, as well as the relationship between time and space in the universe. And so this is really exciting stuff because what is being proposed in this idea is that building off of Einstein's previous ideas of general relativity, as well as ideas in regards to the Big Bang and the birth of space and time, and things like that. And it's kind of building off these ideas and trying to create a model that represents something that's accurate and is really able to answer a lot of the issues that we see when we're looking at different models, such as the Big Bang and things like that. And so this is kind of pretty groundbreaking stuff that we have here, and it's just really exciting to be able to partially learn a little bit more about that, and it was definitely one of the reasons I was so interested, is because it wasn't necessarily a lecture on old stuff, but it was a lecture on the history of these ideas and how they've been built upon most recently. So, the main points of his lecture regarded the discovery of general relativity, which dates back to Einstein's revolution, and a lot of different new ideas that were coming out, and how the truth can be revealed through general relativity. And then it accounts for a very large array of fascinating astrophysical phenomena. And so being able to apply that to a real world model. And then the next major point that Professor Ashtekar addressed was that of the Big Bang and the birth of space and time and general relativity. This really had a lot to do with application of general relativity to the universe as a whole. And in that, we see a lot of issues that the idea of general relativity doesn't really account for when we're looking at the idea of the Big Bang. And so the issue of the beginning was of an argument between the finite beginning and no beginning or end, no singularity. And so at the Big Bang, we have this situation where the space and time continuum tears and classical physics stops. And this is a little bit difficult to address when we're trying to explain that through general relativity. And so it continues on through the Big Bang and understanding it from a mathematical and physical standpoint. And from there, we're able to go into the third major topic, which is that of physics beyond Einstein. And when we're going from the Big Bang to the idea of the Big Bounce. And so that's kind of the outline of the lecture, was definitely this idea of building off of general relativity and going in towards how we can understand things like the Big Bang and how this model was developed, and then going even beyond that and going into the idea of the Big Bounce. And so the one thing that I want to talk about today is the idea of the Big Bounce. And so this is a new idea that instead of, I wish I had the diagram up, instead of this idea that the universe had a finite beginning, it's more of this idea that the space and time is almost bouncing back and forth. And so this is based off of quantum gravity, and there's a lot of conceptual difficulties there. In general relativity, to the general lessons that gravity is very important to the geometry of space and time. So we have this understanding, and understanding that quantum gravity is quantum geometry. And so being able to have this idea of gravity in space and time as a geometric representation. And so when we're getting into quantum gravity, we're faced with some questions like, what are the atoms of geometry and how do they fit together to give us a continuum under normal circumstance? And can quantum gravity provide us with equations that still hold at and beyond the Big Bang, where the continuum tears and classical physics stops? And this is the big question that we're trying to answer through this lecture. And so we figure out that it quantum geometry becomes so important when Einstein's continuum completely breaks down. And that is something that's really difficult to understand. And so it addresses, quantum geometry addresses this new idea of how we can address this point in the Big Bang, or this point in this continuum where classical physics breaks down, and how can we figure out a model in that instance. And so then at that point we are able to get into loop quantum gravity. And so basically the hallmark of loop quantum gravity is that it retains Einstein's fusion of geometry and gravity, but uses quantum gravity. And so it's not only matter, but its space and time are also quantum at birth. And so brand new mathematical and conceptual tools to do physics without space-time continuum. And this is groundbreaking because we're able to set up a model that is valid when classical models break down. And so we're able to see that through this fabric of space woven in a one-dimensional quantum thread, quantum geometry is polymer like Einstein's continuum, while Einstein's continuum is only a prediction. And so this is really interesting because it's almost taking the points at which Einstein's theories are not able to address certain things, and then taking points where the Big Bang isn't able to address certain things, and coming up with a model that actually fits much better and addresses issues with both of these concepts, which is amazing. And so there is the fate of the Big Bang of gravitational relativity and loop quantum gravity. And so what happens to the equations of loop quantum gravity at the Big Bang? They don't break down. And so there's major departures from Einstein's equations near the Big Bang. And it's an unforeseen brand new physics. And so the idea is that the space-time continuum tears, but the thread is very precise. And so we're able to use that in loop quantum gravity, and the Big Bang is therefore replaced with the Big Bounce, which is a major shift in the issue of origin and the beginning. And so the idea is that the repulsive force of quantum geometry is extremely strong, but short-lived. So it's almost this idea that we have the Big Bang, but there's another side of the Big Bang. So if you're looking at a graphical representation of this, you get what's almost an hourglass figure. And so this idea that space, like the equations once we get to the Big Bang, are actually bouncing back and forth in this idea of creation. And so it's the idea that there's a pre-Big Bang branch joined to our Big Bang branch by quantum gravity. And so we have these ideas of new quantum forces, neutron star, and it's a novel quantum force associated with matter that can combat gravity and halt gravitational collapse. And then quantum gravity is therefore the completion of that. And so the Big Bang singularity of gravitational relativity is tamed when we get to loop quantum gravitational idea, and it's replaced by a big bounce, where there are physical quantities that are finite. And this really introduces a new physics, and addresses how gravitational relativity is incomplete, and it addresses these incompletions in a new way. And so to summarize again, the three major points of this public lecture was the history of Einstein's gravitational relativity, and how this model is incomplete because it ignores quantum physics that's crucial in the early universe, and its prediction that the Big Bang is the beginning can't be trusted because of that. And then we get into the next topic, where impressive advances over the past 2 decades by taking into account quantum physics into the cosmological classical spacetime inflation leads to a successful paradigm to account for tiny fluctuations needed as inputs. And these are very, very small fluctuations, like super small. And so loop quantum gravitation has quantum matter as well as geometry from the start, while Einstein's continuum is an approximation which breaks down near the Big Bang. But LQC does not break down. And that's one of the major points of this lecture. And it's something that's really exciting. So I hope I was able to teach you a little bit more about LQC. I know it's a topic that I've never heard about before until this lecture, and it's something that definitely interested me a lot. Yeah, so I hope that I taught you a little bit about that. And in addition, this definitely makes us question other things in physics, and perhaps how we can apply LQC to modern physics, and how this type of understanding of applying quantum materials and quantum physics can be used in the future to address other discrepancies that we're seeing in a lot of our major models that we're using, even in things that aren't necessarily cosmological. If we're looking at maybe things in physical matter, or relationships between atoms, and just really being able to address things using new and different ideas, and try to come up with a model that represents all of these accurately and doesn't break down when we see a lot of our classical physical equations breaking down. So yeah, I'm excited to see what the future holds in this regard, but thank you so much for watching.